Welcome to session 8 of network theory. We will discuss the application of Laplace transforms to network theory today. The previous couple of sessions focused on the solution of networks using differential equations. Specifically, we discussed a first order differential equation as well as a second order differential equation. And we also took some examples of applying a step function as an input. And what we noticed was as you keep increasing the number of elements, the circuits get very cumbersome, the mathematics gets difficult. In fact, we did not do much math. We borrowed the existing math that people have developed over the centuries. And what we did is we just applied those differential equation mathematics, and nevertheless we found things were getting quite difficult for us. So what we are going to do in this session is look at Laplace transforms as a tool to replace differential equation mathematics. Okay. So in the simplest case, let's consider the two networks below. The first network is basically a simple resistor network. It has two elements, R1 and R2, and you're applying some current, AC current source. Therefore, it is a current varying as a function of time. I should call it I of t. But when you write a small I, it usually indicates AC. And this AC current source is a forcing function. Okay, this circuit as it is with R1 and R2 is a passive network. It cannot generate energy. So I'm applying a forcing function, which is given by your current I of t. And this current then causes the current flowing through the resistors induces a voltage. And what we are trying to characterize is what is this voltage. I know what is the current. Okay, I'm connecting the circuit to an oscilloscope and I'm applying some current. And now I want to see what is the voltage response. So if you look at the equation below, what's shown is that V is equal to some function I times R1 plus I times R2, right? Because the voltage drops across resistor 1 and resistor 2. So the total voltage drop across the terminals, as shown over here in the figure, is that it is I times R1 plus I times R2. And therefore, as I've demarcated over here, the voltage is the response. The driving function is I of t. That's what's driving the circuit. And this is a transfer function, which is an algebraic equation. Because when I write I of t times R1 plus I of t times R2, I can take I of t out and it becomes R1 plus R2, right? And this is trivial stuff. We know it. The point is that we work with various network theorems. We used, reciprocity theorem, Thevenin's theorem, and all of those worked out very conveniently for us when we were working with resistors. The moment we started introducing inductors and capacitors, things got difficult for us. So if I look at the same circuit here, instead of R1 and R2, I've replaced the resistor with R and one inductor L. And the same forcing function is being applied, the same I of t. And I'm looking at the response V of t. Okay. And the equation is given by I of t times R. That's the voltage drop across the resistor. And the voltage drop across the inductor is L di by dt. Okay. So if I were to group these terms together, I can take I of t outside. And here I'm left with R plus L di by dt. So d by dt is an operator. Okay. It's not a number. R is a number. So let me write that. I mean, although it's obvious, let's just have it there. Number, L is a number, D is an operator. It's performing an operation. Okay. So what I have here is a differential equation as a consequence of this mathematical operation, which is different from an algebraic equation. So this is an algebraic equation, this is a differential equation. Let's highlight that. And the differential equation needs to be solved like we did in the last couple of classes by finding out what is the complementary function and then the particular solution by applying boundary conditions, right? So we solved it. We know what is the answer of this network now because we have solved it a few times. And we know that the current is, I think it was something like I is equal to I naught or I of 0 into exponential of minus RT over L. And we said that L over R is equal to tau, which is the time constant, right? We know this stuff. And if you do not make sure you have solved it sufficiently that this automatically pops up into your head, because these are very standard circuits. Now, the way we got to this exponential equation is we knew that there was something called as a characteristic equation. We knew that the general solution is a1 exponential of minus alpha t. That was the general solution of such kind of differential, first order differential equations. And therefore, we were able to progress because somebody developed all that math for us. And then, as you went to second order, things got a little more difficult. What we are going to talk about today is the Laplace transform, which helps you transform a differential equation into an algebraic equation. Okay, that's the main. The Laplace transform does many things, but as electrical engineers working on this network theory course, the main thing that's of use to us is the Laplace transform takes this differential equation over here and converts it into an algebraic equation. Okay, so this is Laplace. The algebraic equation can then be solved by simply solving something like this. And once you get the answer, you can again convert it back and get the original answer. Okay, so this is the response. Like what I mentioned earlier, when I said that V of t is the response over here. So this is that response V of t. And we discussed this example in the earlier, right? We talked about this logarithms. We talked about the logarithm table and in the introductory lecture. If not, let me quickly show that. So when we talked about the log table, we said that if I want a function, let me take some space over here. So Laplace equivalence to logarithms. So when I said that I have a variable c is equal to ab, then I can write that log c is log a plus log b. Find out what is this and then take antilog c. That's the answer. Okay. And in the case of Laplace transform, what I'll do is I'll have some equation. So I have a forcing function a forcing function applied on some network gives me some response. Okay. And what the Laplace will do is I can take the Laplace transform of the forcing function. So I take the Laplace transform is given by the symbol. So I take the Laplace transform of the forcing function acting on the network function, and that gives me the Laplace transform of the response. Okay. So this Laplace transform acts on this whole thing. And once I found the Laplace transform of the response, I should find out the inverse Laplace transform of the response and get back the answer. So it's the same thing. If you look on the right side, I have C. Let's say C is the response. C is a product of two numbers A and B. Let's say A is the forcing function and B is the characteristic, is the system function. So I take log C is equal to log A plus log B. I found out what is the value of log C by adding up these two numbers. And then I find the antilog C to get the answer. In the case of Laplace transform, I apply the Laplace transform to the forcing function in the network. And any operation you apply on the LHS has to be applied on the RHS. So I applied the Laplace to the LHS and to the RHS. And using the Laplace transform, I easily solve the problem. And then I find the Laplace inverse of the RHS and get back the answer. Okay. So that's the basic philosophy over here. So let's look at some examples. First of all, let's understand what is the Laplace transform. You know how a logarithm works, that if I say log of some number, say log 10 to the base a, is like saying that a is equal to 10 to the power x. Okay. So when I take log 10 to the base a, that's equal to x. Okay. That means I'm finding out a is equal to 10 to the power what. So x is that answer. For example, if a is 100, then 100 can be written as 10 square. So log 100 is equal to x is equal to 2, right? So that's how the logarithm works. So I'm doing some transformation. What is the Laplace transformation? The Laplace transformation of a given function of time f of t is defined as L, which is that symbol, L of f of t over here is equal to f of s. F of s is just a notation, right? So if I write f of s, it means L of f of t. T is in the time domain, S is in the S domain. What is the S domain? Don't worry about it. We'll look at it later. But the point is, this is just a notation. F of s is equal to integral 0 to infinity f of t times e power minus st dt. So this is the basic Laplace transformation formula. Just like you have a logarithm formula, you say log of a to the base 10 means you're trying to find out a is equal to 10 to the power x, and therefore your answer is x. So if a is 100, a is 10 to the power 2, so log 10 of a is 2. So I'm transforming a number 100, I'm representing it by the number 2. Okay, that was a logarithmic transformation. So in the case of Laplace transformation, the transformation I'm doing is that I have some number, some function f of t. So I'm finding out L of f of t. I'm now transforming that function f of t. F of t, for example, could be sine t, sinusoidal function, some function of time, or it could be exponential of time. It could be any set of functions. It could be a step function. So the Laplace transformation of f of t is given by integral 0 to infinity. There is 0 minus, and don't worry about that right now, but let's remember it's a 0 minus f of t into e power minus st dt. Okay, so this e power minus st dt is that factor which is being multiplied with f of t, and it's being integrated from 0 to infinity, and this is represented as f of s. Okay, so this is the basic Laplace transformation. Now let's take some example. So let's say I talked about step function. The step function is defined as is represented as u of t, and it's defined as a function which has a constant value above 0 and less than 0 to 0. Okay, so u of t is step function as a function of time. I could have had u of x. So u of x, and x can be some variable, say distance. So I can say that, I have a curve, and when the distance is any value greater than 0, then the value is 1. So u of t is not necessarily a function of time, it's just a function of some variable. If the variable is distance, then u could be a function of distance. And if the variable is time, u is a function of time. So in this case, when I say u of t, what I'm referring to is the fact that I have a function which is going to give me some constant value when time is greater than equal to 0. So if I'm trying to find out the Laplace transform of u of t, then I'm applying the same symbol here. I said L of f of t in the previous case. Over here I said L of f of t. So f of t is u of t. So L of u of t is integral 0 to infinity. Now I have put u of t in place of f of t into the same factor, e power minus st dt. Okay. And since I know u of t is what? The u of t function is defined as u of t is equal to 1 when t is greater than 0 and is equal to 0 when t is less than 0. At t equal to 0, it is not necessarily defined, and we'll not worry about that, fine detail right now. So the function is u of t is equal to 1 when t is greater than 0. So u of t, nothing, it does nothing. It basically says that the function is 1. So u of t is vanished now. It's there only from 0 to infinity. And now I'm integrating e power minus st dt. And the integration of an exponential, e power minus st, will cause the factor minus s to come out. So it becomes 1 by minus s e power minus st, 0 to infinity. And this is something you can solve. So when t is equal to infinity, this term becomes 0. So I put 0 here. And when t is 0, then the exponential is 1. So the answer is 1 over s. That means the Laplace transform of u of t is given by 1 over s. Okay. Remember that I had written the Laplace transform as, I said L of f of t is f of s. This is the notation. Okay. Similarly, if f of t is a correct, I of t then the Laplace transform of that is I of s. This is just notation, so that when you're writing these things in your exam or in your notes, you'll remember which is the time domain and one is in the s domain. Okay, the Laplace transform. V of t voltage becomes V of s. Okay. So there is no logic over here. This is just notation, just like language. So let me write that. Similarly, we have other notation also, right? In network theory, with regards to small and capital. When I say I of t as a small number I of t implies this is a AC signal. If I write I, that usually implies DC signal. So these are just notations that you have to keep in mind when you're working with electrical engineering. So we have talked about the Laplace transform of a function, and we have talked about, if I have a step function, then what is the Laplace transform of it? It is 1 over s. Now, what is this s? We don't know what is s right now. In fact, we don't have to worry about what s is. It's just some representation. I have some function u of t in the time domain. It is represented by 1 over s in the s domain. Okay, because our aim is not to find out what is the meaning of this intermediate. What is our aim? Our aim, as we mentioned in this figure in the top here, is that I'm trying to find the Laplace transformation. Once I find the Laplace transformation, I'll solve the problem. Then I'll convert it, I'll use inverse Laplace transform and then get it back to the original value. So I'm really not concerned about what is the interpretation of 1 over s and what that means for us at this stage. Later on in the course, we will actually go into it and we'll understand what is the meaning of complex frequency, and it will relate to your earlier knowledge of phasors and things like that. So we've performed the Laplace transformation of a function. Now we want to find out what is the inverse Laplace transform. So the equation for that is given by f of t is 1 over 2 pi j. J is the square root of -1, the complex number. Then there's integration from sigma 1 minus j infinity to j infinity. F of s, which was the Laplace transform, e power st. Remember, in the first case, it was exponential of minus st. Now it has become exponential of st ds. I suppose that you have either started your Fourier transforms already in signals and systems, or you will soon be starting. And this whole formalism will hopefully become clear to you when you read signals and systems. And even if you are not very clear about it, don't worry. The topic here, as I wrote at the very top, is applications of Laplace transform. It is not the theory of Laplace transform. So all we need to know is that I have a differential equation. I want to convert it into an algebraic equation. So the differential equation came up because we are using inductors and capacitors. And the moment I bring inductors and capacitors into the circuit, it becomes complicated to solve it because there's a lot of heavy math involved. Therefore, to make life easy, we are using Laplace transforms to convert the differential equation to an algebraic equation. Once I've converted to an algebraic equation, for example, R1 plus R2, then I can just add it up. I can say V is equal to IR, and then I can transform the Laplace transform back to the original time domain. Okay, so the Laplace transform goes back to time domain, and then you will see what the answer is, and that's the beauty of it. Now, a couple of important Laplace transforms. In fact, what I would like you to do as a homework is to solve some of these functions and find out what is the corresponding Laplace transform. And this will also help you for your, it will help you get an edge over the other students in signals and systems because you get to double practice it, both in this course and that course. In the simplest case, we talked about the Laplace transform of f of t is integral e power minus st dt. In place of f of t, if I write df by dt, if I take the differentiation of f of t, so if I plug in df by dt, then what happens is the Laplace transform is now written as s f of s minus f of 0. Okay, that means I'm taking the Laplace transform of f of t. Oops. L of f of t is equal to f of s. So now when I take L of df by dt, that is the same f of s, but multiplied by a prefactor s minus f of 0. Okay. Remember that this is in the s domain. This is just a constant. It is telling me what is f of, this is saying f of t equal to 0. So if I take the original function f of t at time equal to 0 and find out what is the value, that is f of 0. And if I know the Laplace transform of f of s is f of t is f of s, I know this, then the Laplace transform of df by dt is given by the Laplace transform of f of s of f of t, which is f of s, times s, that becomes s f of s, minus the value at f of 0. Now, this looks a little complicated, but don't worry about it. The reason why I have highlighted differentiation and integration here specifically is that you don't have to worry, you don't have to work through it much. Whenever you see an inductor or a capacitor, if you see an inductor, then you will expect to see the voltage is L di by dt. So you'll get di by dt. If if supposing there is a capacitor, then you will see 1 over c integral I dt. So there you will find an integral equation. So it's good to just memorize these values, that if I see an integral function, then the Laplace transform of it is the original function divided by s. If I see the differentiation of a function, the Laplace transform of it is s times the original function minus f of 0. Once at this point, when you're seeing this, it's just like newer and newer formulae, and it's like, just kind of boring. But once you apply it to the circuit analysis, you'll start really appreciating, this formalism. I want to make a point that in the differential equation, when we solved with the differential equation algebra, we said that I'm solving this function by finding the characteristic equation, I find the general solution, and then I have to find the boundary conditions. So from the boundary conditions, I find the value of I naught, right? I say I of 0. You can already see the equivalence of it. When I find the differential equation, this f of 0 is actually a boundary condition. It's like telling me what is the initial condition, initial value of the circuit. So of the applied function. So in the differential equation, you have to solve the equation, find the solution, plug in the values, solve for the boundary conditions, and then you'll get the initial value. In the Laplace transform, in the very beginning itself, you are getting the initial value f of 0. Okay, it will become clearer as you solve some circuits. And in fact, why don't we do that? So let's consider the case of the same RL circuit that we had, on top. Let me just go up here. So this is the RL circuit in series. Okay, and we said that V is IR plus L di by dt. Now let me consider the case that there is no current source. So I'm looking for a homogeneous equation. So with that current source removed, the V is 0. There is no terminal voltage. So L di by dt plus Ri is equal to 0. Okay, the sum of voltages by using Kirchhoff's voltage law. By the way, I noticed when I was reading online that I was misspelling Kirchhoff. It should be Kirchhoff. I used to just put a single H, but apparently in some textbooks it's got a double H. I don't know which one is right, but just make sure you get the right one. So coming back to the main point, if I have this different RL circuit, then the differential equation is L di by dt plus IR is equal to 0. If I take the Laplace transform, now what happens? Consider the formula that we had here with the differentiation. We said L of df by dt is s f of s minus f of 0. Now I have L di by dt. L is a number. Nothing happens to L in the Laplace transform. When I say that I'm taking Laplace transform on both sides, just be careful that the L that I'm writing here is the inductor L. Okay. When I write Laplace transform, the L will look like this. So it's this pound sign, right, with the UK pounds. So the pound sign is a Laplace transform. The regular L which I write is just the inductor. So L is a number. So it's a constant. It comes out of the equation. R is a number. So what is the Laplace transform of R into I? It's just R into I of S. So the original I was I of t. Remember, I don't write the t's, but originally it was a function I of t, and now the Laplace transform is I of S. Okay, and just like I wrote here, so I said I of t becomes I of S. So I of t has become I of s. R is a number which came out. L is a number which came out. And di by dt, di over dt, has become s times I of s minus I of 0, which is the original condition. Now see, the whole differential equation is gone. It has become like a simple equation where wherever you had a differentiation, it has got a prefactor s. So if I were to now solve this, I can say I can take L and S are prefactors of I of S, and R is also a prefactor of I of S. So Ls plus R into I of S is equal to Li0, right? I took L and this I0. I0 is just a number, so it's gone to the right side. And now it has become an algebraic equation. Started with a differential equation, it has become an algebraic equation. So I of S is equal to Li of 0 over Ls plus R. That's equal to I of 0 minus over S plus R by L. This is the I of S. Now remember that when we worked with the differential equation, I said finally the solution is I naught, I is equal to I of 0 e power minus RT by L. Okay, this is the solution of the equation. This is what we are heading towards. We want to come here. Instead, what we have got is, we got the solution that I of S is equal to I naught over S plus R by L. But this S over R by L means nothing to me. It's in some random domain. It's in some other domain. I want to get it back to time domain. So to get back to time domain, what I need to do is apply the inverse Laplace transform and find out that I of t is L inverse I of S, and that should come to be I of 0 minus e power minus RT over L. So how do I go from this step to this step, right? That means I now need to do the inverse Laplace transform. Well, the good news is that we are not going to worry about this inverse Laplace transform equation. Instead, since we are dealing with standard elements like resistors, inductors, and capacitors, we already know most of the functions that we will encounter. Therefore, what we have is actually a table of Laplace transforms, just like you have a log table, right? You say you can go to your logarithm tables. I don't know if you guys ever did it. We did it when we were in school. So we used to have these logarithmic tables. And when we wanted to solve something like C is equal to A plus B, we had to go and refer to the tables, find log A, log B, add it up, and then anti-log of C. So similar to that, we have a Laplace transform table. These are the various Laplace transform pairs. So if my input is a step function, we solved this, right? We said that the Laplace transform is 1 by S. If the input is an exponential function, then the Laplace transform is 1 over S plus A. So if I want to go from the original signal, if I want to find the Laplace transform, then I have to apply the formula exponential of, I have to integrate it over e power 0 to infinity f of t into e power minus st, right? That's the integration we are doing here. If I want to go from the Laplace transform back to the time domain, all I need to do is refer to this table and go to the RHS, find out what is the corresponding transform over here, and that's my answer. So let's see if we can do something like that. For my equation with the inductor, I got the answer as I naught over S plus R by L, right? So this is a function of the form I have some constant, which is I of 0 minus some constant times 1 by S plus alpha, okay, where alpha is equal to R over L. So now I want to find out what is the inverse Laplace transform of this. The constant is just a constant, it's going to come out. So I need to find out what is the inverse Laplace transform of 1 plus S plus alpha. Now, when I did the unit function over here, I found out the step unit step function. The Laplace transform of that is 1 over S. Now, if you look at that 1 over S, the only difference is here I have 1 over S plus alpha. So there's an extra alpha term in the denominator. Let's see if we can find out what is the inverse transform of this on this table. So here is the transform. exponential of e power minus alpha t into u of t is given by 1 plus s plus alpha. Fantastic. So our answer is 1 over s plus alpha. So what is the inverse Laplace transform of this? The inverse Laplace transform is e power minus alpha t into u of t. Therefore, what is alpha? Alpha is r over L. So this is e power minus rt over L into u of t. See, we got back our original answer. Where did we get this answer from? We had solved it using the RL circuit over here, right? We had solved this differential equation using this RL circuit. And now what we are saying is that if I were to use the Laplace transform, I can convert it to an algebraic equation, find the inverse Laplace transform, and I get back the answer very easily. See, we completely bypassed using differential equations. We did not have to find any complementary function. We did not have to, substitute and find the boundary conditions. None of that happened. It all happened in one clean step. To appreciate this, like I said before, we'll have to do several circuits. Let's do one last example for today, which is the transient response of an RC circuit. Okay. So I have a resistor, capacitor, and I have a voltage, a DC voltage V0. Let us assume that there was a switch over here so that at time t0, the switch is turned on. Okay, so there is a switch here which is turned on at time t0. Before t, the circuit was off, open circuit, nothing was happening. At time t is equal to 0, I close the switch. What does that mean? My input is what? My forcing function. Let me call it the forcing function so you can remember the terminology. My forcing function is V0 into u of t. It's a step function, right? Because before t is equal to 0, the switch was open. At t is equal to 0, the switch is closed, and therefore it is V0 into u of t. Now I have to solve this equation. I times R is the drop across the resistor. I'm now following Kirchhoff's voltage law. So I'm taking the sum of, no, I'm doing Kirchhoff's current law over here. So what I'm going to do is, let me see what I've done here. So 1 over c integral I dt is voltage. So I've actually used Kirchhoff's voltage law. I don't know why I wrote KCL. So let me erase that selectively and make it KVL. Okay. Just to be thorough about it. So we are taking the sum of voltages in the loop is 0. So I into R, the current I of t is flowing in the loop, right? I into R plus 1 over c integral I dt is equal to u of t into V0. We said the forcing function is V0 into u of t. Take the Laplace transform. So Laplace transform of I of t, I of s. See, it may be surprising to you to see, at least I found it funny in the beginning to say that the Laplace transform of I of t is I of s, which means nothing, right? Something happened. We don't know what happened. We integrated I of t from 0 to infinity multiplied by e power minus st or something. We are not seeing any of that. I know the definition, but I'm actually not seeing any of that. I'm simply changing the notation. I'm saying I of t is equal to capital I of s. That's all. Now, in the other case, when I have integral I of t, so here I have I of s, and what was the formula? Integral of f of t is f of s divided by s. So I have I of s divided by s, and 1 over c is a constant, so it's just sitting out there. And then u of t, what was the Laplace transform of u of t? We said it was 1 over s, right? Where did we solve that? Up here. So we said the Laplace transform of u of t is equal to 1 over s. So on the right side, which is the forcing function, v of v0 into u of t became v0 over s in the Laplace domain. Let me write it since it's probably the first time you're seeing it. So to be explicit, this is time domain and this is s domain. Okay, I did not intend to change the color over here. Go back to black. From time domain we converted to Laplace domain by saying that there is I of s into r plus 1 over cs I of s is v naught over s. So what's the equation? I of s, I take it on the right side and club all the terms on the left side and club the terms on the right side. What is v naught? It's a constant because I said v naught into u of t. U of t is the function, v naught is a prefactor. So v naught is a constant divided by s, and here I have r plus 1 by cs. So that's gone down here. And if I take the s inside, then this becomes v naught by r into 1 plus s by s plus 1 over rc plus 1 s plus 1 over rc. Yeah. So now if I want to find the Laplace transform of this, what's going to happen? This implies I of t is Laplace inverse of I of s. That's v naught over r is a constant times exponential of minus p over rc. Remember, for the inductor, what did we do? We said that I have some constant over s plus r over l. Okay, I have s plus r over l, and s plus r over l became exponential of minus rt by l. So s plus 1 by rc is going to become exponential of minus t by rc, right? And then there is a u of t. Let me write it out. So here is u of t. This is my answer. I can proudly highlight it. And what is the physical meaning of this? Finally, you know, all this math we are doing as network theorists should relate back to the network. And we want to make sure, you know, it's agreeing with whatever we had put over here. So according to our network, at time t is equal to 0, I close the switch. That means the circuit is turned on. Before t is equal to 0, there was nothing, right? So what is my answer? My answer is I of t is something into u of t. That means when t is less than 0, there is no current flowing in the circuit. After t is greater than 0, u of t is equal to 1, right? So then u of t vanishes. It's just a number 1 multiplied with the rest of the term. So all it is ensuring is that before time t is equal to 0, there is nothing flowing in the circuit. After time t is equal to 0, there is some current flowing in the circuit. Now let's look at the other terms, v naught by r. So v naught over r is the current which is, you know, flowing in the circuit, and it is reduced by a value given by e power minus t by rc. So if t is equal to 0, that means at time t is equal to 0, instantaneously, I close the switch, and at that instant, what happened? At t is equal to 0, this exponential vanishes because e to the power 0 is 1. U of t is 1, so both of these terms are gone, and you're left with only v naught over r. That means at t equal to 0, instantaneously when you closed it, the current flowing in the circuit is given by v naught divided by r. Why is that? Because you know that the capacitor by nature is a short circuit for AC. So at that transient stage, when I've just closed the switch, at that very instant, the capacitor is like a short circuit, and the entire voltage drop is across the resistor, and the current is given by V by R. Then as time increases, the capacitor starts charging. So as the capacitor starts charging, the current starts reducing, because we discussed this in the beginning, right? We said that as the capacitor starts charging, a voltage develops across the plates of the capacitor, which is opposing the forcing function. And due to that, the voltage across the capacitor increases. And because the voltage across the capacitor increases, what is the current? So let's say that there is some voltage across the capacitor Vc, and there is a forcing function V naught. Then that implies current I is equal to what? V naught is a constant. Vc is a function of time. It's increasing as the capacitor is getting charged. The current then becomes V naught minus Vc by R. Is that correct? Because the current flowing is given by the voltage drop across the resistor divided by R. Simple as that. So I of t is V naught minus Vc by R. And that's what is coming out of this equation over here. Our final answer is telling you that initially I had V naught by R, because at time t is equal to 0, this Vc is 0. And then as time increases, the Vc keeps increasing as the capacitor is charging. And so Vc minus V naught reduces. That is, the voltage across the resistor reduces, and the current flowing in the circuit therefore reduces. And finally, what happens at t is equal to infinity? the entire applied voltage finally drops across the capacitor. The capacitor gets fully charged, and therefore the circuit breaks. You know that the capacitor is an open circuit for DC, and indeed, that's the answer of this, the solution of the circuit, that the capacitor is an open circuit. So at time t is equal to infinity, there is no current flowing in the circuit. So therefore, this is called transient response, right? We are talking about a DC voltage, but we are talking about the transient behavior. That means I just turned on the switch, instantaneously, how does it behave? So initially it behaves as a short circuit, and as a function of time, it becomes an open circuit. So we used Laplace transforms to solve this integral equation over here. There's no differentiation. So an integral equation, we converted the integral equation to an algebraic equation in the S domain. From the algebraic equation, we quickly found out what is the value of I of S. Using the Laplace transform table, we found out what is I of t, and it perfectly explains our circuit. So in the next class, we'll do some practice problems using various functions, and make sure you thoroughly understand Laplace transform, because subsequent units of the course, we will now, understand in terms of Laplace transforms. Okay, so thank you for hearing today's class, and see you soon in the next class.